Okay, aloha and good evening, everyone. Thank you for joining us for this evening's Hawaii Webb Space Telescope Connection Talk. We'll be learning about Hawaii, the eyes of JWST, how JWST's infrared eyes were developed right here in Hawaii. But before we start that talk, I'd like to tell you about some upcoming presentations we have that you might be interested in. On Wednesday, December 1st, we'll have the next talk in our series of Hawaii Webb talks, which will tell us about the future of infrared detectors beyond the James Webb Space Telescope. And it'll be streaming again at youtube.com/UHIFA or the same Zoom URL. So we welcome you to join us here after Thanksgiving and learn more about what's coming in the future. And our last Hawaii Webb talk will be on some of the science being done with James Webb with Chris Ashall, one of our IFA astronomers, talking about dissecting exploding stars with James Webb Telescope. He's one of the few astronomers who actually have two approved programs in the first cycle of James Webb Space Telescope observations. So we've got plenty of great science with James Webb to tell you about. But before we do more of that, tomorrow night, there is a almost total lunar eclipse, and we will be live streaming it, weather permitting, from 10 p.m. to midnight, right here at this same YouTube address, youtube.com/UHIFA. So we hope you'll join us. You are also welcome to go outside and enjoy the view through binoculars or telescope or just naked eye. Tell your friends, tell your enemies, everyone can join in. So let me tell you a little bit about tonight's talk. My name is Roy Gal. I'll be the moderator for tonight's talk. So I'm doing the introductions and I'll be handling the Q&A at the end. So this talk is titled The Hawaii, the Eyes of James Webb Space Telescope. And our speakers will be Klaus Hodapp, an astronomer at the University of Hawaii, and Shane Jacobson, one of our engineers. And I'd like to encourage you to sign up to follow us on social media or to get our email newsletters at that website that's on the screen in front of you. So a little bit about our speakers. Klaus Hodapp is an astronomer here at the UH Institute for Astronomy. He's at our Hilo facility. He received his PhD in 1984 in Germany. He's been with us at the IFA since 1988, and he's been deeply involved with instrumentation here as our Associate Director of Instrumentation and for our Hilo branch. And he worked deeply developing the Hawaii infrared detectors with astronomer Don Hall, who passed away, unfortunately, a few years ago. And this is what Klaus will be telling us about today. And he's built many of the leading infrared cameras in the world, and he's a co-investigator on the near-infrared camera science team for James Webb. So he is deeply, deeply involved in everything he's going to tell you about today. And Shane, you will see in some of our videos, and we'll be here to answer questions at the end. He's an engineer at the Institute for Astronomy, and he got his Bachelor of Science at USC. And he has been working with Don Hall and Klaus Hodapp in the labs to build and test these Hawaii infrared detectors, including those that were designed to fly on James Webb. So he gets his hands dirty in the lab all the time. So before we start with Klaus's presentation, we have a short introductory video about James Webb Space Telescope and infrared detectors for you to enjoy. If you have any questions, please save them to the end. If you're on YouTube, you can put them into the comments or the chat on YouTube, and we're monitoring that. And then if you're on Zoom, there is a Q&A button on your screen. You can hit that and enter your question, and we'll be asking those and asking them out loud to our panelists at the end of the presentation.
The launch of NASA's James Webb Space Telescope, or JWST, heralds a new age in astronomy. The The telescope will be transported by rocket 1,000,000 miles into space, farther than the orbit of the moon, to become the premier space observatory for the next decade and possibly beyond. Once it reaches its destination, JWST will unfold like origami, expanding 18 hexagonal mirrors to collect photons of light for 4 state-of-the-art instruments, providing data to help solve mysteries of the universe. JWST will build upon the vast accomplishments of the Hubble Space Telescope. This is one of the Hubble's most famous images. Thousands of galaxies imaged within a minute area of the sky. The JWST is anticipated to reveal even greater details of the universe, with much larger mirrors and updated technology. Its infrared capabilities will break through dense clouds of interstellar gas and dust, peering towards extrasolar planets to detect evidence of water and other signs of life. Cutting-edge technology needed to capture those images traces back to the University of Hawaii at the Institute for Astronomy, or IFA. Throughout the decades, UH astronomers Klaus Hodak and the late Don Hall pioneered the development of sensitive infrared detectors. This technology will enable JWST to gaze deeper into space than ever before. Image-enhancing detectors, called Hawaii 2RGs, are the product of years of work Hall and Hodak conducted with engineers and technicians inside IFA's state-of-the-art labs. On Mauna Kea, the detectors are also at work inside a number of observatories here, helping telescopes see at infrared wavelengths. IFA instrumentation engineer Shane Jacobson began working with Hall and Hodak in 2002. He's responsible for testing and characterizing the detectors in his lab at IFA Hilo.
Typically, when we get a detector in the lab, we'll put it inside one of our craft-set instruments, and we'll have to replicate the conditions of space as much as possible.
More technological advances are developing inside IFA's labs. Its rich, innovative tradition continues to thrive.
All right. So now Klaus will take over and share his presentation with us.
Okay, I'm taking over here. Let's rewind my presentation to the start and actually play it. So, aloha and good evening, everybody. After this beautiful, but maybe slightly brief introduction in the video, I want to go into a little bit more detail on what we have been doing and why these detectors are so closely related to Hawaii and why they're actually, in fact, called Hawaii arrays worldwide. I need to advance to my next slide. So let me start by overall introducing what is infrared radiation. Why do we care about it? Infrared radiation was discovered a little over 200 years ago, precisely in 1800, by Sir William Herschel in England, as part of his studies of the general properties of light and energy. So what he found was essentially an experiment where he dispersed sunlight with a prism, creating a little spectrum. And somewhat to his surprise, he found that with a thermometer as an objective measuring instrument for energy, he could detect that there was some form of energy arriving beyond the region of the spectrum where his eye could see light. And yeah, he drew up this graph of there is something there beyond. Here's the visible light that you could perceive with the eye. There is something there. At the time, it was an open debate whether this is some entirely different form of radiation or whether it's related to light. Now we understand, yes, it's essentially related to light. It's the same thing, just at longer wavelengths. But for Herschel, that was a new territory that was open for exploration, and the answer was not yet clear at the time. Bottom line, 200 years ago, a bit more, the infrared light was discovered. And the overall graph here shows that the visible light that we can perceive with our eyes is actually a very, very narrow range of the overall electromagnetic spectrum that ranges on the extreme end from gamma rays, highly energetic forms of light, of electromagnetic radiation, out to very low energy radio waves. The visible light is a very small part. Infrared is a more substantial region. That is, however, rather difficult to observe. For the visible light, we have our eyes. We then had, for about 100 years or so, photographic plates to use. And then now we have a variety of good detectors, both TV-type detectors and now semiconductor detectors that are visible there. The infrared has historically been just more difficult. So why do infrared astronomy in the first place? And here I sort of separated it, the good, the bad, and the ugly. Let's start with the good. Infrared radiation has the property that it can penetrate dust. Now, we think of space as largely empty, but it's not. In all areas that are particularly interesting, there tends to be an accumulation of dust. Dust is associated with gas. And not to get the impression wrong, it's different from household dust that we can see with our eyes. It is a finely distributed matter, more like smoke. And similar to smoke, it has the property that it absorbs short wavelengths much more strongly than long wavelengths. If you've ever looked through dense smoke, you see that it's reddening, for example, the light of the sun that tries to shine through it. So that's one property that we need infrared for. We need infrared radiation to look at very high redshift objects, galaxies in the very distant universe that move away from us due to the expansion of the universe at substantial speeds, and therefore their whole light is shifted over to the infrared. And intrinsically cool objects like brown dwarfs or young planets that are still hot, basically lava balls or hot gas balls, are mostly observable in the infrared, because the infrared is heat radiation in some sense. It is emitted by bodies that are too cool to emit a lot of optical radiation, but emit most of the energy at these longer, less energetic wavelengths. And then the practical thing, seeing the atmospheric turbulence that distorts images, is a little better in the near infrared, and adaptive optics actually does work in the infrared, while it does not yet really work at optical wavelengths. So here is a beautiful nighttime image of Mauna Kea with two of our biggest telescopes there, the two Keck telescopes pointing their laser guide star systems to a place in the sky where you don't see much optical light. This region of the sky is, as you might guess, the center of our galaxy that is hidden behind dense interstellar dust clouds. And what they are doing there is, I guess, a reasonable assumption that they're just doing Nobel Prize winning work on the galactic center. Specifically, at infrared wavelengths, you can actually, as I said initially, penetrate those interstellar dust clouds, these smoky, thinly dispersed clouds of interstellar material, and actually see the galactic center showing up here as a dense accumulation of stars. And if you combine the advantages of, first of all, seeing through the dust, and then being able to do adaptive optics at infrared wavelengths with the largest telescopes that we have on Earth right now, among them the Keck telescopes, you can do wonderful work on pinpointing individual stars near the galactic center and over the years following their motion. And what you learn there is, in this particular case, that many of these stars have orbits and motions around a center of gravity where you don't see anything. And that is good evidence that this mass there in the center of our galaxy is indeed a supermassive black hole. And that was indeed the work that won last year's Nobel Prize in physics by Andrea Ghez and a competing group from Europe under Reinhard Genzel. So this is very important work at the forefront of science that is only possible at near-infrared wavelengths. The other thing, the second argument was we see objects only at high redshift objects, we see only at infrared wavelengths. Now, go on a little time travel with me and imagine we travel back to the early phases of the universe, a few 100 million years after the Big Bang. The first galaxies are forming. And if you were sitting or flying in space next to one of these newly forming galaxies, you would see a chaotic arrangement of stars, not yet the big spiral galaxies that are characteristics in our present-day universe. They haven't formed yet. We see chaotic groups of very young, energetic stars that emit lots of their light at ultraviolet wavelengths, very short, very energetic wavelengths. The problem is, surrounding these galaxies is neutral hydrogen, and neutral hydrogen tends to absorb this ultraviolet radiation. So if you were sitting there, you would, at visible wavelengths with your eyes, see the galaxy just fine. But if you try to use an ultraviolet detector, well, it would basically see a fog that had absorbed the radiation from that galaxy. Now, fast forward to today's universe. We are far away from these galaxies. Now we see them over a distance of 13 billion light years, and due to the expansion of the universe, at very substantial redshifts. So whatever you saw at visible wavelength has been shifted into the infrared. What you saw at ultraviolet wavelengths originally when sitting next to that galaxy has now been shifted at optical wavelengths. So the net result is at optical wavelengths, where, for example, the Hubble Space Telescope can do its work, you don't see the galaxy because you're looking into that fog of neutral hydrogen absorbing the radiation from the young stars. Nothing comes through, you don't see the galaxy. So if you look at, say, the Hubble Ultra Deep Field, nothing is visible at the optical channels. And only in the two infrared channels that the Hubble has now, you begin to see something there, the first traces of that young forming galaxy. So if you want to study the earliest, youngest galaxies in the universe, those things that formed a few 100 million years after the Big Bang, then you can only do that at infrared wavelengths. And that was the original reason why the James Webb Space Telescope was planned and was beginning its development process. Its main mission was to see these extremely young galaxies in formation. So that's the second big reason why we want to do infrared astronomy and go through all the trouble of making it work. Then, yeah, finally, first of all, adaptive optics, as I mentioned, works best at infrared wavelengths. So when we want to look at objects very close to other objects, like a planet next to a star, we first of all have to concentrate the light of that star into a tiny spot, as tiny as we can make it. That means technically reaching the diffraction limit of the telescope. We then have to use all kinds of image processing tricks to subtract as much of this bright star as is possible. That was done here in this example, for example. And so there's just a little remnant here of uncorrectable radiation from that star left after all these subtraction tricks. And then, yeah, here we see a planet, and similarly in another image, here we see a planet showing up. These are young planets. They are still warm. They're not really hot enough to emit a lot of optical radiation, but they emit infrared radiation. So that's the advantage of infrared being able to show intrinsically cool objects. And finally, then, the example on the right is an example of a deeply embedded young star, where, again, the combination of infrared to actually see through the clouds of dust And the high resolution that we can achieve from the ground enables us detailed studies of, say, this jet of material that is being ejected from this young star and bubbles of material blowing away from it. So high resolution work on intrinsically cool and dust enshrouded objects. So that should be enough motivation. Lots of interesting astronomy is happening in the infrared. However, from the ground, infrared astronomy is just plain difficult. The reason is, well, infrared radiation, as I mentioned initially, is heat radiation. So the telescope itself is warm. It is at ambient temperature. So in some sense, yeah, we are blinding ourselves by the warm telescope and by the warm air in front of the telescope. The sky is in general bright in the infrared because the atmosphere itself is emitting a lot of additional radiation, additional to thermal radiation. And the atmospheric transmission is variable and intermittent. We don't see all the wavelengths very well. Even from a good site like Mauna Kea, that it has been selected and chosen for its elevation so that we are above a lot of the atmosphere, its dryness, so that we have little water vapor in the air to absorb radiation, and its relatively coolness, so that we have little of that thermal radiation. Even there, on Mauna Kea, the atmosphere in the infrared is far from clear. So here's wavelengths in the unit that infrared astronomers like, micrometers, millions of a meter. Visible light is here, and in the visible, the atmosphere is pretty much transparent throughout. There's no colored fog anywhere in the visible part of the spectrum. But in the infrared, the atmosphere is more and more characterized by deep absorption bands, by water molecules and carbon dioxide molecules, mostly. We know usually in public discussions these days, the opposite effect is being discussed, of these molecules actually preventing infrared radiation from the ground of being re-emitted into space. And therefore, these molecules are responsible for the greenhouse effect that leads to the warming of the Earth. On the, for infrared astronomy, we are sort of dealing in the opposite direction. We are looking at radiation coming from space down to the ground. And these very same molecules present a problem for us. So absorption is a problem and emission is a problem. This is a spectrum, again, in microns, in the near infrared from 1 micron, the beginning of real infrared, through the near infrared. You see that the sky is bright from emission lines first, from various molecules in the higher atmosphere. And then at longer wavelengths, even from 2 microns, that is about 4 times the wavelength of visible light, to say 14, 28 times the wavelength of visible light. The background, that is the number of photons that the environment emits into the telescope and therefore overwhelms the faint signals that you might see from the sky, goes up by a factor of, in this scale, 10 to 100,000 or so. It's getting really terrible here. Sometimes I tell my students, if they want to remember how bad infrared astronomy at thermal wavelengths is, it's as bad as optical observations during the day with your telescope on fire. So it's not a pretty picture. That gets us to the ugly. The obvious idea, the simple idea would be, okay, well, then let's leave Earth, go to space, and have all these problems behind us. The problem is space projects are very expensive. You just can't do that easily. In the end, the James Webb cost about $10 billion now, up to its launch and the early phases of its operation. That is $30 for every man, woman, and child in the United States. So it is actually a really expensive project. These big missions also take a long time to develop. The James Webb now took over 25 years with all the delays that it had and so on. That is a major part of somebody's career. So that's why everybody on the science team now for James Webb is rather gray-haired like me. So most of us have spent most of our careers preparing for this. And to some degree, the technology at launch is already becoming obsolete, because you can't just make an upgrade to the technology of a space telescope in the last minute. You can't walk up to the launch pad and change a detector, just as a silly example. But you can't even do this 3 years before launch or 5 years before launch, because everything is already set and planned, and there's no way you can make a last minute change to the complicated instrument. So nevertheless, I mean, James Webb had the basic idea that, say, in contrast to a warm telescope like the Hubble Space Telescope, you can get over all these difficulties of ground-based astronomy by moving away from the Earth into space. Well, fine, Hubble does that too. Secondly, to cool the telescope, and ideally to do this in a passive way that doesn't require expendable cryogens that have a finite life expectancy and at some point are exhausted. So do this as a passively, radiatively cooled space telescope, which is done by shielding the whole telescope with a large sun shield, this big thing down here, so that in the shade of that sun shield, the telescope itself and its instruments cool down very far down, close to absolute zero. We typically use the Kelvin scale, and the telescope then is at 37 Kelvin, that is 37 degrees above absolute zero. You can express this in centigrades, in which case you get to this silly number of minus 233 centigrades. So that's a basic concept. The next thing is a video that I want to show you again of the launch of James Webb and its unfolding.
The James Webb Space Telescope is the largest
It's difficult.
space telescope
It's a complicated
ever built.
project.
Its tennis court-sized sun shield, along with its 21-foot 3-inch primary mirror, will enable Webb's instruments to see back in time to when the first stars and galaxies formed after the Big Bang, more than 13 billion years ago. But Webb's size is too big to fit into any existing rocket, so it's designed to be folded like origami, so it fits inside the almost 15-foot wide payload fairing of the very powerful Ariane 5 rocket. Once in space, the Webb telescope is slowly unfolded in a well-choreographed series of deployments. The solar panel is deployed first to provide power. About 12 hours after liftoff, Webb's thrusters are fired in what's called a mid-course correction burn to fine-tune Webb's trajectory. About 24 hours after liftoff, Webb's high-gain antenna is deployed, enabling communication with ground controllers. Webb is traveling so fast, it passes the moon in about 2 days. Here, a second mid-course correction burn sets the spacecraft on course toward its orbital destination. On day 3, special pallets holding Webb's folded sun shield deploy. First, the forward pallet, then the aft pallet. Webb's central tower is extended, lifting Webb's telescope and instrument package to its operational location. Webb's momentum flap is deployed. As the sun's solar pressure pushes against Webb's large sun shield, this flap helps stabilize the telescope. Special covers hold Webb's tennis court-sized sun shield in place during launch. These covers are now released, freeing the sun shield for deployment. The first of Webb's sun shield mid-booms deploys, unfolding and extending one side of the 5-layer Kapton sun shield. Then, the second sun shield mid-boom deploys. Once both booms are fully deployed, the center rim is deployed, and the sun shield is slowly tensioned. This separates the 5 layers. On the sun-facing side of the telescope, a radiator shade deploys to protect Webb's spacecraft systems from the sun's heat reflected off the sun shield. Near the 10-day mark, the MIRI instrument's cryocooler is started. It begins lowering the MIRI instrument's temperature to about 6 degrees above absolute zero. Controllers now begin the process of deploying Webb's optics. Webb's secondary mirror deploys first. Then, an additional radiator panel behind the telescope deploys. This helps remove more heat from the spacecraft. About 12 days after launch, the first wing of the primary mirror is rotated into place. A few days later, the other mirror wing is rotated into place. About 30 days after launch, another mid-course correction burn further tunes Webb's course toward its final operational orbit, about 1 million miles away from Earth. For the next several months, optics engineers using Webb's NIRCam instrument will align and focus Webb's 18 primary mirror segments into a perfect monolithic mirror. It will take about 6 months before Webb is fully ready to capture its first science image.
Well, you've seen how that simple idea turned into something very complicated. And as I said, very expensive. So that's the complications that $10 billion buy you. Now, after all this effort, we have gone away from the atmosphere. We are out in this distant L2 orbit away from the Earth and its own heat radiation. We have shielded the telescope behind that sun shield and it has cooled it down. We have built a system of unprecedented potential sensitivity. But now we also need the detectors to actually exploit that sensitivity. If we launch this telescope with relatively poor detectors, like the ones that we have been using for a few decades now for ground-based astronomy, then we wouldn't fully utilize the extraordinary opportunity that the design, the coldness, and distance of James Webb out of the atmosphere would buy us. So that's where we come in at UH. We were, in fact, one of the teams doing detector development work for quite some time before James Webb. And then at a critical time, when NASA had to select the detectors for James Webb, it turned out that our team, together with our industrial partner, Teledyne, were actually the winning team. And it's our ideas that have now flown into the James Webb Space Telescope. All but one of the detectors on the James Webb are the ones that we developed. So let me tell you this story a little bit. And unfortunately, at the beginning, I give you a lecture in semiconductor physics. Sounds terrible. But let me briefly discuss what these things are, these materials that allow us to build these infrared detectors. Semiconductors are things that are somewhere between metals and insulators. That's why they have this strange name, semiconductor. Sometimes they conduct, sometimes they don't. And they are found mostly in the center column of the periodic table. The material on top of that column is carbon. And carbon, in the form of diamond, is a particularly stable insulating material that has nice optical properties and makes good jewelry and so on, but it's also the hardest material. And the reason for that is that these materials in the center column of the periodic table have 4 electrons in the outer shells of their electron structure. And it so happens that in atom physics, a configuration with 8 electrons shared is particularly stable. So when these atoms with 4 electrons on the outer shells combine into a crystal, and each atom holds hands in some sense or shares an electron with its neighbors, it forms a particularly stable configuration where every atom has in some sense access to 8 electrons and achieves this desirable configuration of having somehow 8 electrons close by. But they do this by sharing. And these bonds that are formed this way are particularly strong. That's why diamond is the hardest material. Under it is the somewhat larger atom of silicon. And silicon is sort of the semiconductor that is used in the semiconductor industry for commercial electronics and for most everything else. Silicon has exactly the same electron structure as carbon, except that it has 1 additional shell of electrons further in, but the outer shell is 4 electrons. So it forms the same type of crystal as carbon does. with distinctly different properties. Because the atom is larger, the electrons are not as strongly bound as the ones in carbon are. So when you form that crystal, the bonds between the individual atoms are far less strong. So silicon is not as hard as diamond. And while in diamond you need hard ultraviolet radiation to rip an electron away from these bonds, in silicon it's actually fairly easy. The absorption of visible light can rip an electron out of these bonds with the neighbors. At elevated temperatures, even at room temperatures, simply the wiggling around of atoms in the crystal structure liberates or breaks away some of the electrons from their bonds, and then they become freely movable. And freely movable electrons lead to conduction. So a semiconductor, prime example being silicon, is a material that at absolute zero temperature has the properties of an insulator. But at elevated temperature, or when exposed to optical radiation, becomes conductive. So it's an interesting transition case. Below it, germanium, it has similar properties to silicon. It's not as used as much in electronics industry because being an even larger atom, it's more sensitive to temperature. Tin is even theoretically a semiconductor, but in practice at ordinary temperatures, it acts like a metal. And finally, lead, the largest here in this column, is so large that the electrons are so loosely bound that they break off easily, and always some free electrons in the crystal lattice so that it acts like a conductor at all temperatures. Let's focus on silicon. In the electronics industry, you can play a neat trick with semiconductors, and that trick is doping. By introducing additional material into a pure silicon. Phosphorus is a good one, and boron are good examples. Phosphorus has one extra electron. So if you build phosphorus atom into a silicon crystal, then you create a place in that crystal where there is one additional electron that really shouldn't be there and has no place in this bonding scheme of being tightly bound. So that that additional electron is very easily removed from its location and can travel freely. So that means a region called a p-doped region, that an n-doped region here, phosphorus makes an n-dope because it's one additional electron, makes it conductive because it has easily movable electrons. Similarly, on the other side, if you use boron, then there is one electron less. And that defect of having one electron bounding to the neighbor not happening leads to a defect in that bonding structure of the electrons. And these defects can travel around, basically by one atom stealing an electron from its neighbor. So the defect travels around, and semiconductor physicists call this a hole. Yeah. So the interesting effect happens when you place two of these materials together. The electrons here, in the superfluous electrons in some sense, in the n-doped region travel over to the other side, fall into the holes, and recombine with the holes, and everybody is happy. Yeah, the excess electrons have gone away, the holes are filled. That leads to a region where we call it a depletion region, where these extra conduction electrons are again neutralized by the holes. So that depletion region is again insulator. And by virtue of the leftover atoms here having a charge, you actually build up an electric charge in that depletion region. And that comes so conveniently when you want to detect a photon. I mentioned already in silicon, these electrons bound in that crystal are fairly easily dislocated and ripped away from their bonds. So if you actually absorb light in one of these crystals, you rip one of these electrons off its bounds and make it freely movable. And you also create a hole that can also move. The built-in electrical field in that so-called PN junction has the nice effect of instantly separating the electron and the hole from each other. They get torn apart in different directions. So In principle, when you have a PN junction in a semiconductor and illuminate that with light, the weekly line here symbolizes light, and H nu is physicist jargon for light, then you actually create a current that you can measure with an external ampere meter, if it's large enough signal. So that's the fundamental underlying principle of all optical detectors using silicon, and by extension also of all detectors that use different materials, different semiconductor materials from silicon. But all our technology of cameras that are ubiquitous these days, everybody has them in their cell phones, in their cameras, in their whatever rear view cameras on their cars. So the world is full of little cameras these days, and they all work by this basic principle of a PN junction separating out electron hole pairs in a semiconductor. Silicon is only sensitive really to visible light. If you want to use want to detect infrared radiation, you have to use different materials. A good one is a combination of indium and antimony that in combination, well, one is to the left of the middle column, one is to the right of the middle column. In combination, they form an infrared sensitive semiconductor. Another competing one that we're going to talk about a little bit more is mercury, cadmium, telluride, a combination of 3 different metals that in combination again make a pretty interesting semiconductor for infrared radiation. Up to now, we've only discussed a single detector element with a voltmeter or ampere meter attached to it. And that shows me here 36 years ago, a younger version of myself, using exactly such a system at a telescope that I was working on at a time at the Max Planck Institute, doing a single measurement on one point on the sky with a single detector based on this principle that I just explained, a PN junction in a infrared sensitive semiconductor, indium tumanite in this case, and then some electronics attached to it to amplify that signal and measure it. I'm just looking at the ampere meter here and taking a reading here in this picture. You can imagine how laborious it was at the time to take measurements of extended objects and get some sense of the spatial structure of an object. So here, well, these are my 5 data points on extended object. And I'll just show you a picture of how this object actually looks when you look at it with a real infrared camera. Well, we got the structure roughly correct. Yeah, okay. But this is a modern infrared camera. This image was impossible to take in 1985. At 1985, this was the state of the art. So, well, the desire was to build infrared cameras with more than a single pixel. An infrared camera consists of 2 parts. The infrared sensitive material that consists just of individual PN junctions forming the individual pixels. And that's called the intrinsic or extrinsic detector array here. And then some electronics called the readout integrated circuit that amplifies the signal, stores and accumulates the signal, and ultimately reads the signal out to some output amplifier to present it to in computer readable form for storage. It turned out you can't just build the readout integrated circuit in an infrared sensitive material directly. It doesn't work that way. You have to use a silicon based semiconductor piece to build this piece of amplifier and data storage electronics. So the solution for infrared detectors is to actually combine the infrared sensitive material for detection and the silicon material for amplification and readout, and then combine these 2. Combining those 2 involves growing little columns of indium on both sides, micron size, smaller than the width of a human hair. We grow these indium columns. Indium is a malleable material. Then you take those 2 components, align them with a precision of a micron or 2. In customary units, that's 1/10,000th of an inch. very high precision for those who are dealing with mechanics. You align those two and then squeeze them together with a ton of force. Now that sounds difficult, and it is difficult, and it didn't work initially. A lot of development went into this. The first few of these so-called hybrid devices had the nasty habit of disintegrating once you started cooling them, because they're dissimilar materials and there was mechanical stress forming. But in the end, our industrial partners managed to overcome these problems and build sizable infrared arrays in this hybrid technology. So we at UH started out this process of working with industrial partners in developing infrared arrays as part of the competition in the mid-80s to late 80s of HIMSS, which was the Hubble Imaging Michelson Spectrometer, our project and our proposal, versus NICMOS, the Near Infrared Camera and Multi-Object Spectrograph, a University of Arizona project. Our detector array, this was a test array, a very, very small array, was only 8 by 8 pixels, but again, it was larger than a single pixel. It was an ambitious design of the readout integrated circuit. Actually, as it turns out, too ambitious for our own good. Because one thing that we had overlooked at the time is that electronics, when they operate, emit light themselves. We are now familiar with this effect in these LED lamps that these days you can buy, and that are a much better replacement for the old incandescent light bulbs. But yeah, current fed through a PN junction can produce light. Current fed through these readout integrated circuits produces light. So in the end, we found out that we had produced a detector that was perfect in many respects, but unfortunately was blinding itself with too much of this glow coming in from the electronics themselves. A lesson learned. Nevertheless, this device was somewhat useful, and we got some useful results out of it. The example here is, because it was so small, we could read it out fast. And here we observed the occultation of the galactic center by the moon. So we saw one source in the galactic center disappearing after the other and could measure their size that way. The paper actually is from Doug Simons, our current director of the IFA, myself, and Eric Becklin, one of the pioneers of infrared astronomy, back in 1990 when we used this array. Now, well, having made this mistake in the detector design, we lost that competition. The University of Arizona won, and that's why the NICMOS instrument then flew on the Hubble Space Telescope. But as a consolation prize, NASA decided to give us a few of these devices to try them out so that they have an independent source of testing results. And we then very quickly developed the camera and put it into operation on our own 80-inch telescope on Mauna Kea. We were the first. University of Arizona was too busy building the space instrument. So we turned out to be the first to have these things on the telescope. And when we did, this large detector array actually had more infrared pixels on the sky than the rest of the world combined. So that gave us a huge advantage for a few years. And it was the first infrared array that produced beautiful images of the sky, in this case here of a star-forming region. We then proceeded, when we had the next opportunity with funding, to produce the next size up in infrared arrays, to produce the so-called Hawaii series of detectors. And you can't just name a detector after your home state. You have to come up with a clever acronym that just happens to be the name that you want to have. So we decided on mercury cadmium telluride astronomical wide area infrared imager, which so happens to be the name of our home state. So that's why these things are called Hawaii arrays. All over the world, everybody knows them by that name now. So the first one that we developed was the Hawaii 1, a big step from the NICMOS devices with 256 by 256 pixels. This was the 1000 square, the 1 megapixel sensor, and many new technologies were invented to make this work. It was at the time the absolute peak of what could be produced with the silicon fabrication technology at the time and with the material growth technology at the time. Then a few years later, we expanded that to a 1000 by 2000 device, simply to demonstrate that the technologies exist to go to physically larger arrays. And that all opened the pathway to our development for the Hawaii 2RG devices that are now the detectors of choice for James Webb. By the way, Hawaii, of course, I explained already, 2 means 2000 by 2000, and RG means reference pixel and guide mode, two features of the device that were useful for James Webb. We discovered lots of things in the process, and one recurring nightmare was these multiplexer glow sources. So the first Hawaii array here shows these strong light emitting effects from the output amplifiers, but we also had planned for that already and had implemented techniques in the design of the readout integrated circuit to mitigate these effects. And this was, in some sense, our main contribution to this development. The fabrication was done by our industrial partners, but the careful evaluation of these devices, testing them to the absolute limit of their performance, figuring out solutions by operating characteristics, setting voltages differently, and so on, to existing problems, and pointing out to the manufacturers where the problems are and what could possibly be tried to mitigate these problems and work around them. That was our role. And the industrial partners very much appreciated that detailed evaluation. I just want to reminisce a little bit about the first light night of the Hawaii 1 detector. It was an absolutely remarkable night that I will never forget. It so happened that comet Shoemaker-Levy 9 in 1994 was approaching Jupiter and was on a collision course with it. And we had timed our first light for the detector to coincide with these Shoemaker-Levy 9 fragment impacts on Jupiter. So yeah, it was our first light with a new instrument, completely new built camera. We also had at the same time first light on a new optical element on the 8-inch telescope, a so-called tip-tilt correcting secondary mirror that allowed us to correct for image motion and thereby sharpen the images. Those two systems miraculously, in retrospect, worked perfectly in the first night. So then Jupiter's moon Io slowly moved close to the planet itself, which gave us a reference source for our tip-tilt correcting mirror. And when everything worked at the same time, we took this beautiful shot of the mushroom clouds essentially left over from the impacts of these comet fragments on Jupiter. Keep in mind, Jupiter is about 10 times the diameter of the Earth. So what you're seeing here are essentially mushroom clouds the size of the Earth. It was a pretty impressive event. There were other firsts in that night. We transferred our data over to Manoa via the then brand new Ethernet connection that we had to our headquarters in Manoa. A team of astronomers there, Len Cowie was involved, Richard Wainscoat, processed the data, produced this beautiful image from our raw data, and printed out on the then brand new color printer. The resulting color print, Richard Wainscoat put in his backpack, so I was told, jumped on his motorcycle, drove down to the TV station, and we had the image on the 10 o'clock news that night. An unforgettable experience. So, well, after this, again, I mentioned that the path then was open for the development of the Hawaii 2RG detectors. But it wasn't that we had just could do this out of our own funds. What really was set up there was what I would call in retrospect the battle of the semiconductors. At the time, around 2000, it was clear that the mercury cadmium telluride mixed semiconductor material was clearly inferior to the more established indium and antimonide material. But we pointed out to NASA that maybe that's not cast in stone, that new technologies are available to make mercury cadmium telluride better. And one huge advantage of that mercury cadmium telluride mixed semiconductor material is that by changing the mixture of mercury and cadmium, you can actually adjust its sensitivity range to what you exactly need. Mercury is the larger atom with less strongly bound electrons. So by having more mercury in it, you extend the wavelength coverage range to lower energy light to longer wavelength infrared radiation. So that's an advantage. And we pointed out to NASA that they should please give new technologies for making mercury cadmium telluride a chance and not settle on indium antimonide right from the start. So in the end, NASA awarded 2 competitive development projects, one for indium antimonide, one for mercury cadmium telluride. We partnered with Teledyne Imaging Sensors, our industrial partner, to produce mercury cadmium telluride detectors based on a new material growth technology called molecular beam epitaxial growth on Katzing telluride substrates and subsequent removal of the substrates. This sounded all very complicated, and it was indeed new technology at the time, untested, but we succeeded. And in the end, it came down to the fact that our detectors achieved the same beautiful performance as indium antimonide, but at a slightly higher temperature. And for James Webb, hidden behind its sun shield and passively cooled by radiating its energy out to space, a few degrees make a lot of difference for the engineering. So the engineers were so happy that we solved their big problem with the telescope cooling and gave them a little bit more margin on the detector performance. And therefore, we won. And the detectors that we developed jointly with Teledyne are now the James Webb detectors. Here again is sort of the whole history again going from the Hawaii 1 detectors, the Hawaii 2s, which were an older version of mercury cadmium telluride, and then Hawaii 1R, Hawaii 1RG, the Hawaii 2RGs that fly on James Webb, and additional detectors that we developed since with different funding for ground-based work, primarily the Hawaii 4RG 4,000 square detectors in 2011, and similarly the slightly smaller Hawaii 4RG 10s in 2008. So this is one of the Hawaii 2RGs, essentially a slightly bluish looking square of about 3 centimeters square with a little bit of electronics on one side. That's how they look. Purchase price for one of these for a ground-based version used to be about $250,000. Space-based versions are more expensive. And to the left is another interesting thing that we developed, the so-called sidecar ASIC, a set of readout electronics to read these devices out directly on one integrated circuit. At the time, around 2000, this was revolutionary technology. These days, you find these things in every cell phone. But at the time, it was a revolutionary development and solved, again, a lot of engineering problems for James Webb. So here's one of the focal plane arrays that is a mosaic of 4 of these H2RG, Hawaii 2RG detectors being assembled into one of the camera modules for the near-infrared camera. This is an image of the near-infrared camera, an instrument built by the, or led by the University of Arizona, and with us, Don Hall and myself, having been team members on that science team. So you see that what at some point started out as a competition between Hawaii and Arizona turned into a very nice collaboration here. In the end, this is a diagram of the focal plane of the James Webb Space Telescope. The various instruments that James Webb has are all on different parts of that focal plane so that they can look simultaneously at different parts of the sky. And all these detectors, except the detector for the mid-infrared instrument, that's a different type of detector, except for this, all detectors on the James Webb Space Telescope are Hawaii 2RG detectors. So yeah, again, that it summarized again. This is the James Webb now again in its final configuration, artist depiction. Hopefully it works out that way. And again, these are the detectors that we built for it. How do you, however, in practice, in the laboratory, simulate the conditions of that space telescope? The space telescope is far away from the Earth, radiatively cooled to space to a very low temperature. How do you actually test detectors like that in the laboratory? And we've made a little video of our instrument engineer, Shane, disassembling one of our test instruments. I want to show you that video and comment on it. Hopefully it starts. Yeah, that is Shane in the lab with an instrument that we call K-Spec. K-Spec is an old instrument. I built it in 1990, originally to test NICMOS detectors. But we have modified this thing many, many times to adjust to different detectors and different testing needs. So that's why it looks like a jumble of parts of different colors. But maybe the positive news there is we are frugal people. We reuse instruments and we save the taxpayer in hundreds of thousands of dollars by not constantly rebuilding from scratch, but using existing instrumentation and adapt them to new needs. First thing that you need to do to simulate space is to cool things. And if you want to cool things on the Earth, the main problem would be that things would instantly ice up. Certainly the water in the atmosphere, and at some point even the nitrogen and oxygen itself would simply freeze out on your instrument. And to avoid that big mess that would destroy our optics and destroy the detector, we first have to keep our detectors and all the optics in a vacuum. So the first thing that Shane removes here in our instrument is the vacuum vessel cover. And what is exposed then is the first radiation shield. It's golden, not because we try to splurge money on gold, but because gold is very highly reflective at infrared wavelengths. So that gold radiation shield deflects back most of the thermal radiation, the heat radiation that comes from the warm vacuum vessel itself. And that would otherwise heat up the instrument and prevent us from cooling it down. So the next level in our getting closer to the conditions of James Webb is the removal of this first radiation shield. Well, that radiation shield is not perfect. Maybe 1 in 100,000 photons will make it through little gaps and so on. Nothing is perfect. So that's why we have a second stray light shield. That one is black now because we're no longer worried about having many photons, but we want to catch the last few. And after removal of this, we finally have a look at the optics of this K-band spectrograph, where we simulate the low flux conditions that you have in a spectrograph instrument on James Webb. Spectrographs disperse the light and therefore also dilute it. That means it's a way of simulating the exposure of the detector to very low light levels. And these are fairly simple spectrograph optics that we built, but they certainly serve the function of simulating a spectrograph for James Webb. So finally, that then exposes the detector that is still surrounded by another shielding to minimize stray radiation coming in from the side. This is not a Hawaii 2RG array. This is already the next type of detectors that we are working on. But Shane is just going to bring in the actual unit that we used for testing Hawaii 2RG arrays for James Webb. This time it was made of copper, which is a particularly thermally conductive material, so that we could cool it very well. And again, you see that around the detector is another tube here that serves as an additional radiation bevel and a filter in front of it to limit the amount of light coming in. And then finally, after all these layer after layer of reducing the amount of light, infrared light that reaches the detector, here is our Hawaii 2RG array at the center of this instrument. Overall, I mean, despite this instrument being relatively old and having been refurbished many times, K-Spec is actually one of the most sensitive testing stations in the world to test infrared detectors for very low light conditions, where light is not measured in watts or anything, but in individual photons hitting the detector. For these types of tests, this instrument that we over the time developed is uniquely qualified. Another thing that we often do is, again, battling this issue of the readout integrated circuit glow, these self-emission effects. So we developed this technique of actually imaging one ROIC in this brownish dual through a set of optics with another infrared camera. And the results of this technique that we are pretty much uniquely using here in Hawaii is sometimes surprising and sometimes a little embarrassing for the manufacturers. This is a device. It's not a Hawaii 2RG. It's something different that we have worked recently on. For example, we found this splotch of strong emission on these readout integrated circuits. And this turned out to be simply a mistake by the manufacturer. They had made a mistake in the mask design of that ROIC. It wasn't intentional. Somebody made a mistake. And we could pinpoint with our imaging technique this defect here to the manufacturer, and it could then, in subsequent iteration, be eliminated. So these are examples of the type of work that we at the University of Hawaii have been doing to support the work that our industrial partners are doing in actually fabricating these devices. And I want to conclude this presentation here with just a few pictures of the people involved. The top picture was taken in 2016 when, in preparation for in the days before a conference in the United Kingdom, we visited a somewhat older observatory. From the left is our graduate student, Danny Atkinson at the time, our engineer, Shane, myself, Don Hall, and another graduate student, Sean Goebbels. That was our core team at the time. And the larger picture down there was taken at this conference a few days later. It includes a few additional people, among others, the head of the company that we are now working with to actually develop the next generation of detectors. And here between near Don, the head of the detector program at the European Southern Observatories, with whom we have, again, over the decades, had a very fruitful collaboration. They are the big competitor of the Mauna Kea telescopes, the so-called ESO telescopes in the Southern Hemisphere, but we had a very friendly and constructive collaboration on infrared detector development with them. With that, I conclude my presentation here and open it up for questions if you have any. Thank you.
Okay, thank you very much, Klaus. So we have Klaus available, and Shane is also with us, Shane Jacobson, the engineer. So you're welcome to ask questions in the Q&A. I think the chat on Zoom might be working, and I also see a question or two coming in via YouTube. So on YouTube, we have a question from actually our friend Alex Tierbo, who's providing the observing for tomorrow night's lunar eclipse watching. So this is all friendly questions. And he's curious about something you mentioned earlier, Klaus. How much does the intrinsic heat of the sensor matter for your signal to noise? You mentioned some of that coming from the sidecar and from the other readout electronics. So to what extent is that the limiting factor?
Well, the detector, when it's being operated, like all electronics, dissipates some heat. That means it produces waste heat. We need to keep these detectors constantly near the operating temperature. And both in our test instruments as well as in the James Webb, these detectors are stabilized to within a few thousandths of a degree to their correct operating temperature. So heat emission from the readout integrated circuit can be controlled quite well by proper cooling and by proper stabilization of the temperature. But the temperature needs to be always quite cold, because at elevated temperatures, all semiconductors suffer from what we call dark current. That is essentially the thermal wiggling of the individual atoms in a semiconductor crystal, breaking loose individual electrons. And that is a fault signal that competes with the detection of light by the detector. So it has to be minimized. Therefore, the detectors have to be very cold. and the temperature has to be very stable so that the level of dark current in the detector is low and stable.
Excellent, thank you. So actually, I have a question for you and Shane. Are you doing anything special for the December 18th launch date of James Webb?
Okay, maybe I answer this. The science team will gather together in an in-person meeting at the University of Arizona. On Arizona time, the launch is scheduled for the early morning hours, 5-something a.m. So we'll all have a very early start on that day, gather together in some conference room at the University of Arizona and bite our nails essentially to see this thing lift off and hopefully reach orbit safely.
I think here in Hawaii, I'll be fast asleep. I'll find out the news in the morning.
You've seen the video of the elaborate unfolding sequence of James Webb. This is the most complicated spacecraft deployment ever tried. There are 160 or so single point failures in this process. So for us, people have mentioned this 7 minutes of terror for Mars landings. For us, it's 29 days, hopefully not of entirely terror, but at least nervous feelings.
Excellent. Oh, someone's asking, how is the telescope tested against the accelerations that it experiences during launch?
Well, like all spacecraft, all space instruments, they go through a long series of tests, trying to simulate the conditions of space and of launch. The launch vibrations and acoustic, that's high frequency vibrations, loads are very significant. Everybody knows that. Rockets are noisy and they vibrate like hell. So NASA has test stations that subject the individual components first, and then the whole instrument to actually the simulated launch conditions that they will experience, plus a little bit of safety margin. And these tests are not trivial. We have found out in the individual vibration tests of some of our assemblies for the NIRCam camera instrument that indeed modifications were needed to ensure that our overall instrument properly performs and survives the launch and is in proper condition after surviving all these vibrations during launch. So it is an elaborate process to verify that everything in the instrument is properly designed and fabricated to deal with these launch conditions.
We have a mahalo from the audience, so thank you. Maybe time for 1 or 2 more questions. Actually, Klaus and Shane, are the detectors that are going into space manufactured differently than the ground-based ones?
Shane, do you want to answer?
Sure, they're a little bit different. The ground-based ones have actually been produced by another manufacturing partner, Hawaii Aerospace, in Oahu. But the flight packages are slightly different. They were manufactured by the actual instrument teams. So it's in principle they could have been similar. The ground-based packages probably could have been used in space, but it might not have satisfied the exact instrument's needs. So not sure if you want to answer any more, Klaus.
Well, I mean, it gets back to the previous question. For ground-based instruments, we don't have to survive launch vibrations. For space instruments, we do. So that changes the way the detector has to be packaged and supported in the instrument. And indeed, one of the problems that we had during early vibration testing was that the design of the package for NIRCam proved to be insufficient. One mask that we had in front of the detector vibrated too much, actually touched the detector and damaged it slightly. So that obviously was a problem that needed to get fixed. And that's something that we don't have for ground-based instruments. So ground-based packaging is easier and therefore cheaper. Space-based packages is a lot more complicated. And that's why space telescopes overall are so much more expensive than ground-based instruments, because you have to take care of so many more problems.
Okay, maybe one last question. Someone who seems quite knowledgeable is asking, if the 4RG detectors were available more than 10 years ago, and with all the launch delays, was there any consideration given to switching out the 2RGs for 4RGs, or were the things too far developed by that time?
Well, the 2011 time for the H4RGs was the first prototype. That first prototype was not yet of science-grade quality. Science-grade quality H4RG detectors have only been delivered to observatories in the last 4 years. Therefore, they came a few critical years too late for a possible upgrade to the James Webb. The two projects simply didn't merge. And the H4RGs were developed by the National Science Foundation specifically for ground-based applications. They were not space qualified. So space qualification, including vibration testing and many other tests, radiation testing, is an additional long step that needs to be taken to bring anything to space. The Hawaii 4 RG detector simply came too late for that. They will be, the Hawaii 4 RG-10s will fly in future space missions.
That's a great place to end. Thank you, Klaus and Shane, because our next talk will be on the H4RGs and the new Saphira detectors that Klaus mentioned at the end of his presentation. And IFA astronomer Michael Bottom and Klaus and Shane will join us on December 1st to tell us what the future holds for infrared detector development here. We can look forward to. So thank you all for joining us. This will be archived on our UHIFA YouTube channel, and you're welcome to watch it back and see our other presentations there. Thank you very much, and see you next time.
Okay, goodbye. See you in 2 weeks. Bye.